Good evening. I'm Tom Tombrello. I'm chair of the Division of Physics, Math, and Astronomy. They've handed me so many announcements to make before this evening's presentation that I hope we don't use up most of the evening doing them. The next thing you'll see in Beckman is on the evening of Thursday, December 1st. It's the Lauritsen Lecture. It's by Professor Ken Dufay of Princeton University. It's the peak of world oil production, Thanksgiving Day, 2005. I think you might be interested in that one. The next presentation in Beckman is by Professor William Goddard, The Coming Revolution in Pharmaceuticals, and that's on January 18th, 2006. The series of lectures for the 100th anniversary of the Einstein Miracle Year have been put on at Caltech, and we want to thank the Office of the President, and in particular Denise Nelson Nash of Public Events for putting these things together so well. Well, now having gotten through the introductions, I've got to try to remember what tonight's about. It's the Watson Lecture. Kip Thorne is speaking on Einstein's General Relativity. I think it's up there on the screen, from 1905 to 2005, warp spacetime, black holes, gravitational waves, and the accelerating universe. Now, you might say that Einstein had a very good year in 1905, though Kip is obviously not talking about what Einstein did in 1905. But it's also true that in 2005, our speaker tonight also had a very good year. He won a Commonwealth Award with people that you might have heard of, like Colin Powell. He's California Scientist of the Year. And all of that is on top of the fact he wins prizes for writing, wins prizes for teaching. He's the Feynman Professor at Caltech. And if I were to go on about Kip Thorne, we really would use up the whole evening. So at that point, I think I'll just introduce our speaker, Kip Thorne.
I always like to begin a lecture with a quotation from my close friend Stephen Hawking. Can you hear me? Good. There were two scientists, physical scientists, in the history of humankind who are the greatest intellects that we have seen in the physical sciences. Isaac Newton and Albert Einstein, and they tower over all of the rest of us, even Stephen Hawking, and far, far over me. Newton lived 1643 to 1727, and he gave us a framework for the laws of nature that lasted for 200 years, a framework based on absolute space, absolute time, forces, accelerations, the things of everyday experience. Einstein lived from 1876 to 1955. He gave us a new framework that supplanted Isaac Newton's framework. It has now been in place for 100 years, and the fundamental foundation for that is what Einstein called the principle of relativity. The principle of relativity is an audacious thing. It is a law that governs the laws of physics. If you can just imagine that, somebody conceiving of a law that governs the laws of physics. What it says is that each law of nature must be the same in every reference frame. And he laid this down in his classic paper on the electrodynamics of moving bodies in June 1905. So here you are running down Colorado Boulevard in your high-speed sports car. And you have a reference frame inside there. And inside this car, you do an experiment to study the laws of nature. For example, you study the Lorentz force law, the force that acts on a charged particle when it's moving in an electric and magnetic field. I sit outside there, and I do out on the street on Colorado Boulevard, I do the same experiment. And we have to get identically the same answers. We have to see that these force laws for electromagnetism must be identically the same for you at high speed in your car and for me out on the street. Well, that's not quite right, because in 1905, Einstein did not yet know how to deal with gravity, and yet we have gravity on Colorado Boulevard and in your car. And so we've got to do what a physicist often does. We do thought experiments where we very easily put you, the car, and me out in interstellar space, and now we redo the experiment. And so you think about that as a thought experiment, and that's the way it really goes. There were some really remarkable consequences in 1905 that Einstein deduced from this fundamental principle. Quite surprising, but they were forced on him just by laying down that principle that the laws of physics are the same in every reference frame. First of all, in your frame, your car looks like that, but when I measure your car in my reference frame on Colorado Boulevard, as the car goes whizzing by, it appears to be contracted in length. Looking at myself in a mirror, I look perfectly normal, but you look at me as you go flying by, and I appear to be contracted in width. In addition, as I look at your clocks ticking away, an ideal clock, the best atomic clock that the world's best clockmaker can make, I see your clocks running slow, but you see my clocks running slow. How is this possible? Well, it has to do with the fact that simultaneity is different for you and for me. So if you put a bunch of firecrackers on the top of your car and you go running down Colorado Boulevard and you set them all off to explode simultaneously, in my reference frame, I will see the one at the back explode first, then this, and all the way up to the front. So what is simultaneous as seen by you is not simultaneous as seen by me. You get a sort of a queasy feeling now. How are you going to do physics if all of these things are so weird? Well, what is this going on? How is this possible? The key issue is that your time turns out to be a mixture of my time and my space. And your space is a mixture of my space and my time. This is quite analogous to the following, that if you have a compass, and it points toward magnetic north, that's not true north. It differs by about 15 degrees or so. And so magnetic north is a mixture of true north and true east. And that's what's going on in space-time with this mixing of space and time that Einstein discovered from his remarkably simple postulate that the laws of physics must be all the same in every reference frame. The bottom line is that time and space are, in his words, relative. I would prefer to use the word personal. You have your time and you have your space. I have my time and my space. They're mixtures of each other, but so they're personal to ourselves. And things look different to you and me depending on how we're moving. Now, all was well and good, and Einstein worked out the consequences, and they gladdened the hearts of his colleagues who had been working in the same direction and had almost gotten there, but not really made the great leap in understanding this mixing of space and time. But then Einstein had to face the issue of the laws of gravity. Newton's law of gravity says that the sun attracts the Earth gravitationally with a force that's inversely proportional to the separation between the Earth and the sun. The separation when? Well, Newton had an absolute time, and so this was an instantaneous separation because there was no issue of a personal time. There was an absolute time, so it was an instantaneous separation. But Einstein had to ask, separation is measured in whose reference frame? Because he had overthrown, or he had claimed at least to overthrow, the idea of an absolute time, an absolute simultaneity. He also had to ask, the separation is measured in whose reference frame, so separations, distances, are different as seen in the two frames, and instantaneity is different as measured in the two frames. So the fundamental bottom line was that Newton's laws of gravity, because they depended on instantaneity and on distance being absolute, his laws of gravity violated Einstein's principle of relativity, and Einstein had a lot of chutzpah. Newton obviously was wrong. And so he set about trying to figure out what should supplant Newton's laws of gravity. It took 2 years for him to have what he later called the happiest thought of my life. he said later, I was sitting in a chair in the patent office where he was working in Bern, Switzerland, when all of a sudden a thought occurred to me. If a person falls freely, he would not feel his own weight. In other words, if I climb up on a table and I fall freely, while I'm falling, I don't feel gravity. I have no sense that gravity is there. Gravity is gone. And so I then know, while I'm falling, I know how to analyze the laws of nature. Because gravity is gone, and if I'm Einstein, I've worked out the fundamental principles of the laws of nature in my special relativity theory in the absence of gravity. And so Einstein was, from this key idea, he was able to analyze then the following question. If you sit there with an ideal clock, the world's best atomic clock, and you've got one attached to the ceiling, how do the ticking rates of those clocks compare? And what he concluded is that time, as measured by an ideal clock on the floor with you, flows slower. Oh, I'm sorry, on the ceiling, it flows slower than on the floor. Do I have the right way around? Well, we'll see. The bottom line was that time is warped. Okay, I know I have it right on the next slide. And when I'm in the middle of a lecture, I have trouble getting myself confused, okay? So let's go to the next slide where I know I have it right because I have to make an argument in the next slide. I have to argue from this warping of time that the rate of flow of time on the ceiling is different than on the floor, which he deduced from the idea that he could do the calculation when he was freely falling, and he knew how the laws of physics behaved. He then deduced then this idea that time was warped. And so I want to look at the issue of warping of time as being associated with gravity then. It's gravity that is responsible for the different rate of flow of time on the ceiling than on the floor. And so I want to think about the following experiment. I take an apple, or I have you take an apple, and you're sitting here in this room, and you take an apple and you throw it in the air in just such a way that it hits the floor 2 seconds later. And the question is, why did it go in this arcing parabola and then hit the floor? And Einstein gives us an answer. He says that the apple takes the path of longest time, that is the fastest ticking, as seen in its own reference frame. I'll return to why he says this, but he asserts that. He says that the apple finds a route that will cause it to have the fastest ticking, so it takes the longest time to get from here to there. Now let's think through what kind of a path that should be to take the longest time. So I have it right this time that the clocks that you have on the floor here are ticking slowly. The clocks up there on the ceiling are ticking fast. And so if the apple wants to take a long time, that is, it has to have a fastest average ticking of its clock, then it wants to get up to the ceiling where time is flowing fast and then get back down to the floor, but it has to do it in 2 seconds as measured by your clocks on the floor. 2 seconds of its own clock ticking. So it just wants to jump up to the ceiling, stay there, and come back down. But no, it can't do that, because it's also true that the faster it moves, the swifter it moves, the slower it ticks, as seen by you. That was Einstein's principle from special relativity. So it doesn't want to go up to the ceiling too fast, because then it would tick too slowly while it was getting up to the ceiling. And so there's an optimal path where it goes up not too fast, but it tries to get to the ceiling where it can tick rapidly and then back down. And there is an optimal path. And so this apple, it feels its way, finding the path that will enable it to have its ticking be the fastest, that it ages the most on that trajectory. Now, this sounds like a crazy, crazy idea, but this was Einstein's idea. And why was it Einstein's idea? Because he asserted that time is warped. At this point, he did not have space warp, but time is warped. And the trajectory of longest time, he said, is a straight line. Now, you're accustomed to the idea that between this point and that point, the line of shortest length is a straight line. He's saying the opposite thing. He says the trajectory of longest time is measured by my ideal clock as I go sailing up and back down. That's a straight line. And that's the difference between space and time. Einstein understood at this point that space and time were a little weird. And in space-time, in the combination of space and time, if you want to go along a straight line, it's the line on which your clock ticks the fastest, ticks the most. And that's the straight line. And so he said, this is a straight line. You say, well, that's obvious, not a straight line. That's a parabola. Einstein says, I'm sorry, but you have just been trained to think in a rather weird way. If you will just look at that from a freely falling reference frame, it's moving along a straight line as seen by you while you're falling and it is falling. And Einstein says that straight lines, as seen by freely falling observers, those are the straight lines of space-time, and he built his theory on that. So this is then the essence of his building a theory in 1912 in which he said that gravity is due to warp time. And that theory, as he developed it, nicely described all that we know about the solar system, the orbits of the planets around the sun, the orbit of the moon around the Earth. It worked beautifully. But there was something wrong with it, Einstein realized fairly quickly. The problem, of course, is that my space is a mixture of your time and your space. And so if your time is warped, then my space has got to be warped, since it's a mixture. And so you can't have just a warping of time. You have to have a warping, at least as seen by most people, however they're moving through the universe, a warping of both space and time. And so in 1913, then, he modified his theory. It took him about a year with the help of his friend Marcel Grossman, learning the mathematics that he needed, mathematics of what today we call differential geometry, to develop his theory with warped space-time. In 1913, he laid down a version of this theory of warped space-time, explaining gravity. But the theory that he laid down had problems. It wasn't totally logically self-consistent, he soon realized, and he struggled for 2 years of very hard work trying to figure out how to deal with this. Finally, November 11, 1915, he gave us the mathematical law called Einstein's field equation that tells us precisely how the matter and the energy that live in the universe, the matter that your body is made of, the energy of the heat that's coming off of the lights in the ceiling, how they all combine together, that matter and energy, to warp space-time. So in 1915, he had his final general theory of relativity with gravity associated with a curvature of, with a warping of space-time. Let me give you a final little description of this law of general relativity in the following way. Suppose that we have a child who throws 2 apples up in the air absolutely parallel. They go up and then they go down. Now, physicists do thought experiments like this every day, and what the physicists will say is, I want to explore the trajectories of those apples, and I don't want to worry about the atmosphere. I don't want to worry about the apples running into the earth and the rock. And so I just imagine the apples are made of something that doesn't interact with the atmosphere or the earth and the rock. Or I imagine that a hole is drilled through the earth so that the apples don't run into the material. So the apples fall, they just fall down into the earth. And of course, Newton says the apples get pulled together because the gravitational pull is toward the center of the earth, and they will crash into each other. But Einstein says those apples were initially moving along absolutely parallel lines, and then those lines cross. And if you have absolutely parallel lines and then they cross, that's not possible in a Euclidean geometry, in Euclidean space. And so Newton says gravity did it. Gravity pulled them together. Einstein says it was the fact that space-time is warped that did it. More precisely, if you have 2 parallel lines on a flat sheet of paper, they won't ever cross. But if you have them on a curved surface, like the surface of the Earth, and they go up from the equator, they cross at the North Pole. Einstein says the crossing is due to, or Newton says the crossing is due to gravity. Einstein says space-time did it. the bottom line is matter warps space-time, and that warping causes gravity, and that is Einstein's general theory of relativity. And that was the step, in modern language of a physicist, those were the steps that Einstein went through in order to deduce it. One of the wonderful things about being at Caltech is you have really interesting people to talk to. And when I want to understand about the history of work in my field of general relativity and the further developments beyond Einstein's early work, I can go just down the street to the office of the Einstein Papers Project, which is led by Diana Kormos-Buchwald, and with Tilman Sauer being the other the most senior editor along with her. And I can talk with them, I can see Einstein's original papers, and I can get a real understanding of the history of my subject. And Diana and I have even supervised a PhD thesis together of somebody, Dan Kennefick, who is one of the editors on this particular volume, who did both a physics PhD and PhD research in the history of relativity. So this is just one of the beautiful things about Caltech, is all these interesting people to talk to. Let me go on now from 1915 and talk about the consequences of general relativity from 1915 to 2005, the past 90 years. An initial issue is that space is warped inside and around the sun and in any other massive body. That's a prediction of Einstein's general relativity theory. And we can understand that prediction by imagining taking an equatorial slice through the sun, just a slice of two-dimensional slice that bifurcates the sun between the northern half and the southern half. And the assertion is that the geometry of that slice will not be the geometry of a flat sheet of paper. It will be warped because space is warped inside the sun. And the warping is depicted here, much exaggerated. You can think of this as being what that slice would look like by somebody who is looking in from a higher dimensional space, a higher dimensional flat space. And so this stuff around here is this higher dimensional, the higher dimensions of the flat space, and this equatorial slice is warped in it. Alternatively, you can imagine taking the equatorial slice out, move it into interstellar space, and it will have to be bent like this in order to accommodate itself to the flatness of interstellar space. The thing that you notice is circumference around here is less than pi times diameter on that surface, and that is the nature of the warping around the sun, though it is much, much exaggerated here. Now, one of the predictions about this warping that Einstein gave us in 1915 is the prediction of the deflection of starlight by the sun. If you have the sun here and a star near it, here is a picture of the warped space of the sun as seen from hyperspace. The star is there, and a light ray from the star moving toward our eye moves along the straightest line it can travel on this warped surface. But that straightest line that can travel on the warped surface, if we project our eye backward, it makes us think that the star is at this location. And so the star appears to be here when really it was much closer to the sun, well, somewhat closer to the sun. And so this was the prediction Einstein gave us, and in 1919, in a famous eclipse expedition, to test this prediction when the sun was blotted out by the moon so that the astronomers could see the star nearby, the prediction was beautifully confirmed to within an accuracy of 20% or so. By 1955, there had been a number of eclipse expeditions, and the accuracy was thought to be rather better than 20%, but the answer was coming out too big. And this is the first example of what I'm going to give you, that in the history of the development of the consequences of Einstein's ideas, it has taken decades to get to where one could test them with high precision. And here, 1955, that's 40 years later, the precision is not much better, and the answer seems to be coming out wrong, and that was the year in which Einstein died. But he had firm confidence in his prediction and maintained that there had to be something wrong with the observations. In 1970, there was pioneered at Caltech a new technique for making these measurements, a technique based on radio astronomy, radio interferometry. And that technique by 2005 has given us an accuracy of 1 part in 10,000 on this deflection of starlight, beautifully confirming general relativity. Just a wonderful confirmation to very high accuracy. So we know Einstein was right with an accuracy of 1 part in 10,000. Looking on toward the future, there is a space mission called the Space Interferometry mission that is being developed at JPL. Has been tentatively scheduled for launch in 2009, but that launch date is being pushed back along with everything else in terms of space science at NASA, because NASA is in total shambles at the present time with regard to its science program, which is a separate topic from this lecture. But you'll hear me say this several times again. What SIM is going to be capable of doing is mapping stars on the sky to an accuracy of their positions to an accuracy of 4 microarc seconds. That's 4 1/millionth of an arc second accuracy. That is an accuracy 1,000 times better than the deflection of starlight by the sun, not when the star's rays are coming close to the sun, but when the star is way off in a different part of the sky. And so SIM will see the whole sky warped in terms of positions of the stars by amounts that are 1,000 times stronger than its accuracy. And so that shows you where the technology is taking us, to the point where this will have to be dealt with in order to understand the observations. You've got to correct for all this warping. Another example of the influence of warping is what is called gravitational lensing. These are photographs taken by the Hubble Space Telescope in the 1980s, and you see a strange pattern of galaxies here, sort of a circular pattern, and that turns out to be because there is a massive cluster of galaxies down here in the center that is, whose gravitational field is, or whose mass is warping space, and that warped space is acting like a lens, and that lens is distorting all the images in this complicated but very pretty pattern. So warped space shows up in high precision astronomy, in astronomy measurements looking out at great distances, warped space produced by intervening galaxies, clusters of galaxies. In the 2000s, this warping of space, gravitational lensing, is being used to search for exotic objects in the sky called cosmic strings and machos. It's being used to map something called dark matter in galaxies and clusters of galaxies. It's being used to measure the cosmological properties of the universe. So we've come around to where the warping of space is a key tool for studying exotic phenomena in the universe. One of the greatest challenges of this past century, the 20th century, has been to measure the overall shape of the universe. Is the universe overall, when you average over the lumps associated with galaxies and clusters of galaxies, is it shaped like the surface of a sphere or like the surface of a saddle, or is it flat? And the prime goal of the Palomar Mountain 200-inch telescope, Caltech's big 200-inch telescope, when it went into operation in 1948, was to measure the geometry of the universe in this way by looking at the sizes and brightnesses of distant galaxies and seeing whether they are blown up to larger size than they ought to be or not by the warping of space in the entire universe. That quest failed completely. And it failed completely because what people didn't realize at the time that the plan was laid out was that galaxies eat each other. And they eat each other a lot. They're very cannibalistic. Our own galaxy is in the process of eating the Large Magellanic Cloud. It's a satellite galaxy. And when they eat each other, they change their properties. And so if you see a very distant galaxy, it's also much younger than galaxies today are, and you really don't know what it would look like if you got up close to it. And so this approach completely failed. However, Mark Kamienkowski, a professor here at Caltech in cosmology, came to the rescue along with a couple of other colleagues. What Kamienkowski said is the following. What I'm showing you here is the history of the expansion of the universe on one diagram, running from 10 to the minus 43 seconds of the Big Bang up to something like 15 billion years today. The quest of the Palomar telescope to measure the shape of the universe was out here in the modern era, and the universe is very complicated in the modern era. But if we go back to when the universe was about 300,000 years old, the universe was very simple. It was just consisted of hot gas, plasma, with very weak sound waves, large wavelength sound waves, but very weak propagating through it. And we know a great deal about the properties of those sound waves because they were so simple that it doesn't involve the kind of complicated physics of galaxies and stars and so forth. And so what Mark Kamienowski said is, look here at those sound waves and see whether the sizes of the sound waves are amplified or not by the gravitational lensing by the intervening universe. How do you look? Well, with something called the cosmic microwave radiation, which was emitted by this gas and redshifted into the microwave frequency band as it traveled out to the Earth. So this quest was then taken up by Andrew Lang and his colleagues. Andrew Lang is another professor here at Caltech. And Andrew and his colleagues flew a microwave telescope to look at the sky on a flight around Antarctica. The telescope was called Boomerang. And the prediction was that if the universe is closed like the surface of a sphere, then you would have these sound waves on the sky would be amplified, and you would see a pattern like this with pretty big lumps. If it's flat, you'd see a pattern like that with smaller lumps. And if it's shaped like a saddle, you would see a pattern like this. And there is the pattern that was seen, that Andrew and his colleagues saw, and they found that the universe is flat. So the Palomar quest, Palomar failed, but it did lots of other wonderful things. But Andrew Lang and his team of scientists with Boomerang succeeded where Palomar failed by following Kamienowski's suggestion of looking where the universe is simple in order to be looking at something that one understood very well. Then we turn to the warping of time. Einstein also in 1915 predicted that time is warped. Time slows near any massive body, and for example, near the surface of the sun. By 1955, many attempts had been made to measure the slowing of time near the surface of the sun, and they had not really succeeded. The attempt was made by looking at the spectral lines of light that's emitted from the sun, and those spectral lines tell you about the ticking rate of atoms, so it's sort of like atomic clocks near the surface of the sun. And when the radiation reaches the Earth, you compare them with the spectral lines of the same kind of material here on the surface of the Earth, and by looking at the redshift, you can infer the difference between the ticking rate, or the ratio of the ticking rates on the surface of the sun and on Earth. But it was, the sun is so messy that these measurements were very controversial in 1955 when Einstein died. 1976, marching technology comes to the rescue. Robert Vaisseau at the Harvard-Smithsonian Astrophysical Observatory and his team built a set of atomic clocks, hydrogen maser clocks. They flew several of them in a rocket up to a height of 10,000 kilometers, had identical atomic clocks down at the Kennedy Space Center, and they telemetered back down to the Kennedy Space Center the ticking rates of the clocks up here. And thereby they were able to compare the ticking rate of time, the rate of flow of time at 10,000 kilometers altitude with that on the surface of the Earth. The prediction was that time slows near the Earth by 4 parts in 10 billion. And they confirmed this to an accuracy of 1/100%, 1 part in 10 to the 4. Again, a beautiful confirmation of Einstein's predictions, but it didn't come until 1976. That's 60 years after Einstein made the prediction. It took that long for technology to catch up. Today we have the global positioning system with satellites above the surface of the Earth that send down signals that are basically the ticking rates of clocks up there in the satellites, and time markers for clocks up there in the satellites. And down on the surface of the Earth you have a GPS receiver, and the receiver triangulates on these satellites to determine where you are on the surface of the Earth. These radio signals have to be corrected for the slowing of time on the Earth, otherwise the GPS system would fail if you didn't do the correction right. And a former student of mine, Cliff Will, was asked by the Defense Department to chair a committee to look at whether they were doing the corrections right very early on, because there were questions whether they were really doing it right and whether the system would really work properly. And they got it all straightened out. And so those corrections are put into something that is part of everyday technology now. The correction for the slowing of time is part of everyday technology. And that's what has happened with Einstein's ideas. Not only is there a warping of space and a warping of time in general relativity, there is also a tornado-like whirling motion of space around any rotating body. So if as the Earth rotates, it, according to general relativity, grabs space and sets space into a whirling tornado-like motion. The Earth, of course, rotates at one revolution a day, and that drags space into motion at one revolution every 6 million years. That's some tornado. Nevertheless, it's an interesting effect, and it deserves to be tested. And there is a bank of superconducting gyroscopes now in orbit, a project led by Francis Everett at Stanford University, something called Gravity Probe B, which is currently collecting data. And what Gravity Probe B does is these gyroscopes, they're sitting here spinning on their axes, and the whirling motion of space here grabs that end of the gyroscope and pulls it around faster than this end, because this end is farther away, and so the whirling motion is a little lower. And it's sort of like a leaf sitting in a stream near a bank where the leaf turns because of the differential motion. The water is moving faster out in the center of the bank of the river than it is near the bank, and the leaf turns because of that. And that's what happens to these gyroscopes in Gravity Probe B. A very tiny effect, but they expect to measure this with an accuracy of 1% or better. They're hoping for an accuracy of about 1 part in 1,000. Well, let me turn to the most interesting of all things associated with warped space-time, and that is black holes. And whenever I talk about black holes, I always have to bring my favorite black hole out. So this black hole, if it were a black hole, would not be made from rubber, but rather it's made from warped space and time. And in particular, one way to understand the warpage is that the circumference around this black hole looks like it's about 3 feet. So you would expect that the diameter is 3 feet divided by pi, which would be about 1 foot. But in fact, the diameter is not about 1 foot. It is enormously larger than 1 foot. And that's because space is so highly warped around and inside of a black hole. And we can understand this warping, if I can find here we go. We can understand this in the following way. This is a little analogy. Suppose that we take a sheet of rubber, say a child's trampoline, we put it up on stilts, and we put a rock in the center, and the rock sinks the rubber down like this. And then suppose that you're an ant, and you live on this rubber. This rubber is your entire universe. You're a blind ant, so you can't look out and see what's going on here. All you can do is measure the shape of your universe. And you go marching around and measure the circumference, and then you go and measure the diameter, and the diameter is huge compared to the circumference, and you say, how is that possible? And of course, I know how it's possible. I can see the rock that's distorting the sheet. It's because your universe is warped. And this warping is identical to the warping around a black hole. All I do is change the labels. Now I have the shape of an equatorial slice through a black hole, and I have down at the center, I don't know what, oh, there, I don't know where it went. So I have, and this is a shape in hyperspace now. And down at the center where I had a rock before, I now have something called a singularity, which I'll talk about near the end of my talk. Now, the thing that you all know about black holes is when something falls in, it can't get back out, and it can't send signals out. And the reason for that is the following, that if you fall in, and you're living in this space, so it's now a little two-dimensional you or me, falling in, trying to send microwave signals out with a little microwave transmitter. Once you or I fall through the surface of the black hole, which is called the horizon, the signals get pulled down with me toward the singularity. Now, what is the physics that causes that? What gives rise to everything being pulled down? It's a warping of time. We have the curvature of space that I talked about before, but we also have a warping of time. Time slows as you near a massive body. If you remain at rest just above the surface of a black hole, time at that location slows to a halt compared to time far away. And as soon as you're inside the surface, time is still flowing, but it's flowing in a direction you would have thought was a space direction. It's flowing toward the center, toward the singularity down here. And that's why nothing can get out, because nothing can travel backward in time, at least locally backward in time. At the very end, I'll talk about going backward in time by going out into the universe and coming back. But locally, you can't go backward in time. And so it is the downward flow of time that prevents anything from getting out of a black hole. Of course, the black hole can also spin on its axis, and its angular momentum of rotation drags space into a whirlpool, tornado-like motion. But in this case, it can be a very fast motion contrasted with the motion of space around the Earth. It can be a motion of many revolutions per second around a spinning black hole, a real tornado-type motion. A challenge for the coming decade is to probe black holes in exquisite detail to map out all three aspects of warped space-time around a black hole: the warping of space, the warping of time, and the whirling motion of space. This is what the map should look like according to general relativity. A very precise depiction of that map is seen looking in from hyperspace. This is showing the warping of space, and then the color coding is the warping of time. When you get down to the transition between the purple into the yellow in here, time is flowing at about 20% the rate that it is far away. Down here at the beginning of the red, it's 10%, and down there at the black, it is completely halted, and below that, you're inside the horizon. I've cut off the interior of the horizon in this diagram, so the horizon is there. Remember, this is an equatorial slice. I've lost one dimension, and so this is the dimension of space. If I cut right through the black hole, take an equatorial slice, I have this shape and the rainbow colors showing the rate of flow of time. If the black hole is spinning, that black hole was not spinning, but if the black hole is spinning, the throat is predicted to be much longer. And here, coded in with arrows, is the rate of motion of space, the tornado-like motion of space caused by the spin of the black hole. So those are the predictions. They're very precise predictions from general relativity, and we would like to test them. So how can we see a black hole and map this space-time warpage? Well, the problem is that a black hole is black. It emits no light, no X-rays, no radio waves. So if you want to see this, I think the very best way to go about doing it is by using a form of radiation that's made from the same stuff as the black hole itself, made from warped space and time. And these are gravitational waves, a phenomenon predicted by Einstein using his general relativity equations in 1916. And so, for a concrete example, suppose that I have a small black hole orbiting around a large black hole. And this small black hole goes around and gradually spirals in and ultimately plunges through the horizon of the large black hole. Why does it spiral in? Because it's losing energy. Where is it losing energy to? Well, as you see, there are ripples here. Those ripples are caused by the warping of the small black hole's warpage. As the small black hole goes around and around, it creates ripples in the geometry of space, and those ripples travel out like ripples traveling out from your finger if you stir your finger around and around in a pond or in a bathtub. And those ripples are gravitational waves. They're carrying away energy, and so the small black hole spirals into the big black hole as it loses energy, but they also are carrying a map, a full map, in complete detail. One of my graduate students, Fintan Ryan, proved just before he went off to Wall Street to use the tools of stochastic differential equations, which he had learned at Caltech, to predict the motion of money markets. So just before that, he did a superb piece of work in which he predicted that a full map of the big hole space-time warpage is encoded in these waves as they come out. So we have the challenge of monitoring those waves and making the map. Well, how can we monitor these gravitational waves? Well, let me use an analogy again. Suppose that you have waves on the surface of a pond, and you are an intelligent insect that lives on the surface of a pond with some decent technology, and you decide you want to measure those waves. So you get a couple of corks, and you get a laser and a laser metrology beam, and you use the laser to monitor the separation, the precise distance between those corks. And as the waves go by, those corks move back and forth, and you use the laser beam to monitor them moving back and forth, and you can see that the waves are passing. Well, this is what we do with gravitational waves. Here is a picture of what the waves actually do in the gravitational wave case. If the waves are propagating into the screen, what they do is they stretch and squeeze space in the pattern that you see there. Stretching in one direction, squeezing in the other direction, transverse to the direction of propagation of the wave. So this is one aspect of the warped space-time of a gravitational wave. And so we have a superb experimental team that I'll talk about in a few minutes that is headquartered here at Caltech has built Earth-based laser interferometer gravitational wave detectors that that monitor passing gravitational waves, or are trying to detect and monitor passing gravitational waves by just looking at the stretching and squeezing of space. And what is done is to hang 4 mirrors from overhead supports by steel wires. They're steel at the present time. And when the wave passes, these 2 mirrors will be pushed apart. They basically ride on space as it's stretched and squeezed, while these 2 mirrors are pushed together. In the next half cycle, these 2 mirrors are pushed apart, and those are pushed together. And a technique called laser interferometry that I won't go into is used then to monitor the difference in the separation between these 2 mirrors and those 2 mirrors. And this difference, delta L, General Relativity predicts is proportional to L because it's a stretching and squeezing of space. The farther apart you are, the greater will be the motions. So delta L is some dimensionless gravitational wave field, which is associated with the warping of space, times L. The magnitude that we expect for this gravitational wave field is less than or of order 10 to the minus 21. 0.20 zeros and a 1 after it. This is a dimensionless magnitude. You multiply that by the arm lengths for the instruments that our experimental team has built, 4 kilometers, and you find that these mirrors are moving back and forth by an amount of 4 times 10 to the minus 16 centimeters. And so we have now operational instruments capable of monitoring this, of looking at motions of mirrors 4 kilometers apart to this precision. Now, what is that precision? Let's talk about 1 times 10 to the minus 16 centimeters, which is closer to where the noise is in these instruments. Well, 1 centimeter is about half an inch. Oops, let's do it one step at a time. A human hair is 100 microns. That's 100 times smaller than half an inch. The wavelength of the light that is being used to monitor the motion of those mirrors is 100 times smaller than that. It's 1 micron. You go down by a factor of 10,000, you reach the diameter of an atom. You go down by another factor of 100,000, you reach the diameter of the nucleus at the center of the atom. You go down by another factor of 1,000, you reach LIGO sensitivity. Now, this is a tour de force in high precision technology. It is really remarkable. In fact, I co-authored a textbook, a classic textbook on general relativity in the early 1970s with John Wheeler and Charlie Misner. And in there's an exercise for the student to show that this technique of measuring gravitational waves is crazy. It'll never work. Well, this is the way our team is doing it now. In fact, LIGO is a reality. It has one site in Hanford, Washington, with the laser beams running up and down these tubes. It is a collaboration of about 500 scientists at 40 institutions in 8 nations, with Caltech and MIT the lead institutions, and it's headquartered here at Caltech. It is led by Barry Barish and Stan Whitcomb here at Caltech, and the spokesman for the scientific collaboration, those 40 institutions, is Peter Salson at Syracuse University. It was originally Ray Weiss who started the LIGO project. Ray Weiss, Ron Drever here at Caltech, and I started the project back in the 1980s. And the project owes a great deal to the ingenuity of both Ron Drever here at Caltech and Ray Weiss. Here is the second site in Livingston, Louisiana. And here is the noise curve that we said in 1989 when we submitted our construction proposal that we expected to get for our first interferometers when they went into operation. Plotting frequency from 10 cycles per second, 10 hertz here, up to 10,000 hertz. You notice these numbers. These are the gravitational wave strain, and for those of you who are scientists or engineers, it's the noise, so it's strain per square root of hertz frequency. These numbers are 10 to the minus 23 down in here. This is many orders of magnitude. The blue is where our noise was in August 2005. Almost right on, except for a little corner down here. It's superb performance on the tour de force on the part of the experimental team. 12 days ago, LIGO began its first long search for gravitational waves with these interferometers, these gravity wave detectors. A search that will last for a year or so, of maybe 18 months, in order to collect a full year's worth of data. And we are eagerly awaiting the results of this search. LIGO is designed to look at small black holes in distant galaxies. Black holes with masses between 10 and 100 times the mass of the Sun, sizes of order 100 kilometers, something like the size of the Los Angeles area. We also have in the planning stages, intermediate planning stages, a different gravitational wave detection system called LISA, the Laser Interferometer Space Antenna. LISA is consists of 3 spacecraft which track each other with laser beams, just like we use laser beams to track the motion of these mirrors in LIGO. But these spacecraft are 5 million kilometers apart. So instead of 4 kilometers, 5 million kilometers. And correspondingly, they go after gravitational waves with much longer wavelength. Instead of wavelengths that are of order the size of North America, as LIGO does, or the size of the state of California, they go after wavelengths that have sizes of order the distance between the Earth and the Moon, or the distance between the Moon and the Sun. Much longer wavelengths, a very different frequency band. Correspondingly, they will study, or LISA will study, giant black holes in distant galaxies, black holes that weigh 1 million times what the sun weighs. JPL and Caltech, LISA is, as you see by these symbols up here, it's a joint mission of the European Space Agency and NASA. And JPL and Caltech are in charge of the science from the American end. Tom Prince is the mission scientist for LISA. Sturl Finney headed the mission design team that before LISA became a real mission, and he now, these are both professors at Caltech, he now is in charge of the data analysis and the characterization of gravity wave sources for LISA. I'm also involved. A number of people at Caltech and JPL are involved in LISA, as we are in LIGO. LISA is currently scheduled for launch in 2014. Again, it will probably get pushed out because of the chaos that's going on with regard to the whole science program in NASA at the present time. But LISA has a very high rating with regard to scientific priorities, and so we remain quite confident that it is going to fly. Let's return to what LISA and LIGO might do. One of the pieces of science, mapping a black hole, the space-time warpage. What happens if the map comes out wrong? Well, one possibility is we may have discovered a new type of inhabitant of the dark side of the universe. That is, a new kind of object with highly warped space that emits little or no light, little or no electromagnetic radiation. There are 2 long-shot possibilities. You might have a dense object that's made from cold, dark matter and has a very different kind of a warped space. Conceivably, you have a singularity like the one at the center of the black hole, but it's not at the center of a black hole. It's sitting out in the external universe for all the world to see and has some wildly shaped warped space. I've just made these shapes up out of my mind. These are not predictions. They're just icons to indicate that we could have big surprises when we look out at the universe and start doing these maps. We also will have the possibility to probe the very horizon of a black hole, that point of no return down which things fall, out of which nothing can come, because this little hole raises a tide on the horizon of the big hole as it orbits around. That tide pulls back on the little hole and changes its orbit, by a fairly large amount, and that large enough amount that very easily LISA should be able to see this when LISA looks at the gravitational waves from such systems. And so we actually expect with LISA to be able to probe the horizons of black holes and study what their properties are. More interesting than that to me is the study of two black holes with comparable masses that come crashing together and liberate in explosive energy 10% of the mass of the black hole converted into radiation, into gravitational waves. There is no electromagnetic radiation emitted whatsoever. It's all in the form of gravitational waves. These are the most powerful explosive events in the modern universe. The only thing more powerful, according to theory, the only thing more powerful was the Big Bang birth of the universe itself. And the details of this collision are encoded in the waveforms, the up and down oscillations of the gravitational waves that are emitted. And so I would very much like to see those waveforms and see the details of these kinds of collisions. And let me describe this a little more graphically. Each black hole is rotating, so it drags space into motion around itself. So you have, like a tornado, so you have two tornadoes. They're orbiting each other. Their orbital angular momentum drags space into motion. So you have two tornadoes embedded in a third larger tornado, and you want to know what happens when they come crashing together, when they're made from warped space and time and not made from air. And we don't know. We don't know because we haven't been clever enough to solve Einstein's equations to figure it out. We will figure it out through a combination of the observations of these collisions and supercomputer simulations, as I'll indicate in a moment. Now, how far can LIGO see such black hole collisions? Well, today, with its present sensitivity, it can see out about 250 million light years, out to a distance where there are about 50,000 galaxies. At that distance, there is predicted to be about one collision every 10 years, but this is a very uncertain prediction. It could be bigger, it could be smaller. But we have to be lucky in order to see black hole collisions with our current instruments. A very exciting development in the last week or so has been a deduction from new observations of something called short gamma ray bursts, that although we might not be lucky with seeing black holes, that we could be lucky with something, a different kind of a source, two neutron stars spiraling together and crashing together, or possibly a neutron star being torn apart by a black hole. New estimates for event rates for that just in the last week by Nakar and Gal Yam, who are young astrophysicists here at Caltech, and Derek Fox at Penn State. New number of 3 per year, the first time we've had such an optimistic prediction for initial LIGO. But I don't believe theorists' capability of making these predictions, even when they're guided as these are by observation. And we will look out and we will see. But we're all very excited about the fact that these observations are now underway, the search is underway. In 2010, we will upgrade to advanced gravity wave detectors, which can see 18 times farther through 300 million galaxies to a distance where the best estimates are a 1 black hole collision per day. And so this upgrade was really the instrument we wanted to build in the first place, but it was much too big a leap to go from our 40-meter prototype here on the Caltech campus that was built originally by Stan Whitcomb and Ron Drever to these big instruments with a very sophisticated advanced detector. So we had to do it in 2 steps, and we're now in the first step, and then we will do the second step and do very rich science, we're quite sure, after the upgrade. To interpret the observed gravitational waves, we've got to compare with supercomputer simulations. And so we have developed here at Caltech, in collaboration with Cornell, a project for simulation of extreme space-times, led by Lee Lindblom, Mark Scheel, Franz Pretorius, Lee Lindblom, Mark Scheel, and Harold Pfeiffer. I got the wrong person on here. I apologize if Harold is in the audience. Saul Tukulski and Larry Kidder at Cornell. And interestingly, funded jointly by NSF, NASA, and the Sherman Fairchild Foundation. We are now in an era where when you have an exciting new piece of science that you want to get done, NSF and NASA are no longer nimble like they used to be, and they can't move quickly in and provide the funding at the level that's required to really pick off the great science. And so the Sherman Fairchild Foundation, a private foundation, has stepped in and provided the necessary funding to really bring this fully to fruition. The best simulations to date by anyone in the world are by Franz Pretorius, who was a postdoc in the group. This is just a picture of a simulation then of the warped time around a colliding two black holes that are orbiting each other and collide. And so the black area is where time is slowed right to a halt. That's the center of the black hole, and these other regions are where time is flowing more slowly. This was the first successful simulation of a collision of two black holes. The black holes go around each other a couple of times and collide, and the code is stable and computes all the way to the end. And this was just done this past spring here at Caltech. Here is a picture of the gravitational waves produced in that collision, again from the simulation. You see the waves flowing out as the two black holes merge in a pattern, much like the spiral pattern of waves you would produce if you were to stir your finger in the water. So we're just at the beginning of being able to do these kinds of simulations. There's still a long way to go, but these are going to be key to getting the science out of LIGO. Well, in the last few minutes, I want to move into some other aspects of warped space-time that are more speculative. Let me begin with the singularity at the center of a black hole. General relativity tells me that if I fall into the black hole, the singularity will stretch me from head to foot, squeeze me from the sides, then stretch me from the sides and squeeze me from head to foot, and do an oscillatory stretching and squeezing in a pattern that is chaotic in the technical sense of chaos in mathematics, until I die. And then it will stretch and squeeze the atoms of which my body are made, until they are distorted beyond recognition, and until all matter of which I'm made is completely destroyed in this singularity. In other words, the laws of physics as we know them break down in the singularity. The singularity is the domain of the laws of quantum gravity, and the best candidate for the laws of quantum gravity, a new branch of theoretical physics, is string theory, or M theory, a more modern variant of string theory. We have here at Caltech a superb group working in string theory: John Schwartz, Hiroshi Oguri, Anton Kapusta, and Sergei Grukov, and pushing hard, trying to understand the unification of general relativity with quantum theory in order to be able to discuss such things as singularities at the center of a black hole. Is there any hope to ever do experimental studies of singularities? Well, there's a bumper sticker that you sometimes see on cars that says the Big Bang is a naked singularity. The Big Bang is a singularity that you can see. It's not inside a black hole. And indeed, the Big Bang, if we think of the universe as being like the surface of a balloon blowing up as it expands, coming out of the singularity, there also should have been gravitational waves, and so I show this surface of the balloon with little bumps on it, the gravitational waves. And the holy grail of gravitational wave science is to probe the Big Bang singularity with the gravitational waves that came from the Big Bang and from the early inflationary era of the Big Bang. Gravitational waves are the only form of radiation that can travel unscathed through the matter of the hot primordial universe to today and bring us direct information about the Big Bang. And so Andrew Lang, by a technique involving the cosmic microwave background polarization, and his group is going after this holy grail. At its next incarnation of gravity wave detectors on the Earth and in space, the regular gravity wave experimenters will be going after this holy grail. And I expect that within the next 20 years or so, we will be probing the very birth of the universe with gravitational waves. But that's a time in the future, and that singularity is very far away. Is there any hope to find or make and study singularities in the present-day universe? The establishment has an answer, probably not, and that's embodied in the cosmic censorship conjecture due to Roger Penrose, a great physicist at Oxford University, which says that all singularities except the Big Bang are hidden inside black holes where you cannot see them unless you pay the ultimate price of going into the black hole to explore them, the ultimate price that you can't publish your results. So all singularities then are clothed by horizons, is that what this conjecture says. There are no naked singularities. So John Preskill and Stephen Hawking and I made a bet about naked singularities back in 1991 on one of Hawking's many visits here to Caltech. It says, whereas Hawking firmly believes that naked singularities are an anathema, Hawking is the defender of the establishment, and should be prohibited by the laws of classical physics, Preskill and Thorne regard them as quantum gravitational objects that might exist unclothed by horizons for all the universe to see. Therefore, we make a wager with Hawking putting in some gobbledygook to protect his side of the bet. The loser will reward the winner with clothing to cover the winner's nakedness. Clothing is to be embroidered with a suitable concessionary message. Well, this was the event here in Beckman Auditorium at which Stephen Hawking conceded, though not graciously. This is the T-shirt he gave us, embroidered with what he regarded as a suitable concessionary message, really a challenge. Nature may be allowed to have naked singularities, but nature abhors them anyway. Now, why did he concede? Because of supercomputer simulations. Numerical relativity, solving Einstein's equations on supercomputers, is really the wave of the future in understanding warped space-time. Supercomputer simulations, in this case done by Matthew Choptuik at the University of Texas, in which he sent waves in. These were actually something called scalar waves, but another group a little later did it with gravitational waves. Let me talk about it as gravitational waves. So send gravitational waves in with almost enough energy in them to make a black hole, but not quite. Right on the borderline between making a black hole and not. And what happened in these supercomputer simulations was the waves came in, they interacted with each other non-linearly, and space and time began to boil and froth, a sort of an organized frothing, creating right at the center, ultimately, a naked singularity with infinitesimally small mass that lived for an infinitesimally short period of time, but enough to force Hawking to concede. And so now the challenge is to find out whether or not naked singularities are allowed with big sizes, long durations, formed in generic situations, and we have a new hot bet with Stephen over that. Wormholes. You can't talk about warp space-time without talking briefly about wormholes. You all know about wormholes, at least those of you who watch TV or go to movies, from the movie Contact, Star Trek, Stargate, and other science fiction shows. Basic idea is that we are here near Earth. Our universe is somehow in hyperspace wrapped around like that, so that you can have a wormhole, so-called, that goes through hyperspace that will take us from Earth to the vicinity of a distant star. In Contact, it was the star Vega. And you can travel through a distance that might just be a kilometer, for example, instead of going around 26 light years. Well, together with a student of mine, Mike Morris, I worked out the prediction that in order to hold a wormhole open, you have to thread it with a material that has negative energy. And so there's been a great, considerable effort over the past 15 years since we figured that out to determine whether or not you can get together, in principle, if you're an arbitrarily advanced civilization, enough negative energy to hold a wormhole open in practice so that you can go through it. The answer is not yet in, but things are looking more pessimistic than they did 10 years ago. And this is not our work here at Caltech. About the time that we did this seminal work on wormholes, LIGO got funded, and we put everything behind us to focus our research group's effort on LIGO and let those at other institutions pursue the wormholes. Then there's the question of backward time travel, and this is something that I've gone back and forth with Stephen Hawking on. In 1998-90, I realized that if I have a wormhole, then in principle, it's easy to make a time machine with the wormhole. I have my mouth of the wormhole here. My wife, Carol Lee, has her mouth of the wormhole. She goes out in a rocket ship at high speed around the universe and comes back. And because of something called the twins paradox that I won't go into in detail, it turns out that when she goes out and comes back, it takes an hour as seen by her to go out and back, but it takes a couple of years as seen by me. And the bottom line, because we're actually holding hands through the wormhole at the same time, is that the wormhole gets converted into a time machine in such a way that if I go in this mouth and come out her mouth, I go forward in time by 2 years. If she goes in that mouth and comes back this mouth, she goes back in time by 2 years. I won't go into the details. Those of you who want to see the details of this and some of the other things I've talked about, you can buy my book. It's a little out of date, 1994, but there's a discussion of this, and these drawings are from it. 1990, I did a calculation with a postdoc, Sun-Won Kim, which showed that something called vacuum fluctuations will always course through a time machine right at the moment that you try to activate it and may destroy the time machine. Time machines self-destruct when you activate them. We looked more closely at the strength of the explosion, and they concluded that the explosion was too weak, that the time machines would not be destroyed. Stephen Hawking, upon getting a preprint of our article, before we had, the ink was hardly dry, wrote a paper and submitted it for publication saying we were completely wrong, that the time machine would self-destruct, and he proposed the chronology protection conjecture that nature has a way to keep the universe safe for historians. Over that period, there's been a growing consensus that only the laws of quantum gravity know for sure whether or not you can make a time machine and go back in time. And so Stephen Hawking, 5 years ago on my 60th birthday, gave me as a birthday gift and his first attempt to estimate, using the laws of quantum gravity, the probability that a time machine can be created that is sufficiently big that I could go back in time through it. And that probability he calculated quantum mechanically is 1 part in 10 to the 60th. I responded on his 60th birthday 2 years later with a promise that LIGO will test his black hole predictions for his 70th birthday. And let me end up then just with a description of our extreme ignorance of warped space-time today in 2005. We don't know. Does a black hole have the precise shapes of warping that general relativity predicts? We don't know for sure. What happens when black holes collide? What other objects made from warped space-time exist in our universe? What about singularities? What are their structures, their behaviors? The Big Bang singularity, the singularity in the core of a black hole. Can wormholes exist and be made? Is it possible to travel backward in time? The answers will come from gravitational wave observations, numerical relativity simulations, and the new laws of quantum gravity, string or M theory. We're still exploring Einstein's legacy, and we will continue to do so for many years to come. Thank you.